We present Im2Hands, which is the first neural implicit representation for two interacting hands. Compared to the previous state-of-the-art method that relies on low-resolution mesh representation, Im2Hands can produce two-hand meshes with an arbitrary resolution, learns two-hand geometries with high hand-to-hand and hand-to-image coherence, and does not require vertex-wise correspondences or monoparameter annotations for training. To handle the articulations and interaction contexts between two hands, our key idea is to take a two-stage approach, where we first perform initial occupancy estimation in the hand canonical space, and then perform interaction context-aware occupancy refinement in the original space. Our method achieves the new state-of-the-art accuracy on image-based two-hand reconstruction. We will now discuss the motivation of our work in more detail. The existing hand reconstruction methods can fall into two categories: mesh-based two-hand reconstruction and implicit single-hand reconstruction methods. The mesh-based two-hand reconstruction methods directly regress monoparameters or vertex positions of monomeshes. However, they model hands with meshes with a fixed monotopology, which is not in a high resolution. In contrast, implicit function-based reconstruction methods can learn continuous hand shapes. However, the existing method predicts single-hand occupancy field conditioned on pose inputs. Thus, they cannot incorporate two-hand interaction context or perform image-based reconstruction. This has motivated us to propose Im2Hands, the first neural implicit representation for two interacting hands. To learn continuous 3D occupancy field of interacting two-hand geometry, we train a neural network that maps a query point to the occupancy probabilities for each hand. Our two-hand occupancy function takes as input a shape observation alpha and a pose observation beta, which are represented as an RGB image and sparse two-hand 3D key points, respectively. As mentioned in the overview, our key idea to learn the complex two-hand occupancy field is to take a two-stage approach. We first perform initial occupancy estimation in the hand canonical space, and then interaction context-aware occupancy refinement in the original space. For our initial hand occupancy estimation, we train on MLP-based part occupancy networks to predict occupancy values for each bone part, motivated by the existing articulated neural implicit functions. In this stage, the input query position X is transformed to the canonical space for the current bone part. Here, the canonicalization matrix for bone B, denoted by TV, is computed using the input 3D hand key points using the biomechanical conversion algorithm of Hallow. To model shape and pose-dependent per-hand deformations, our part occupancy function takes per-bone global shape and pose features, each extracted from bone lengths and canonicalization matrices, respectively. Here, we additionally propose to use per-query shape feature to recover fine-grained shape details observed from an image. To this end, we introduce query image cross-attention to extract a per-query feature while attending to image regions more informative for estimating the occupancy at the current query position. While the initial occupancy estimation models hand geometries robust to various articulations by learning them in the canonical space, it is non-trivial to model two-hand interaction context. Thus, we propose to use a context-aware occupancy refinement network to modify the initial two-hand occupancy in the original space to enhance hand-to-hand coherence. To effectively encode the initial geometry of two hands, we first represent them as point clouds, which are sets of isosurface points of each hand. These points can be easily obtained by collecting 512 farthest points among the query coordinates evaluated to be on surface by our initial hand occupancy network. Then we encode each hand point cloud into a global point feature and locally anchored point features using point transformer-based architecture. We then apply cross-attention between a query, local point features, and a context latent vector to estimate a refined occupancy value. Here, the context latent vector is extracted from the global point cloud features and the input image to provide two-hand interaction and image contexts for the refined occupancy estimation. Now, we further consider image-based two-hand reconstruction using Im2Hands. As mentioned earlier, our model takes as input an RGB image and two-hand key points. We also consider a scenario where only image inputs are available and the hand key points are obtained from an off-the-shelf image-based key point estimator. To enable more robust reconstruction in such scenario, we additionally introduce an optional key point refinement module that can alleviate input key point prediction error. where the refined key points are estimated via multi-edit attention between key point features encoded using a graph convolutional network and the input image features. To train our network, we consider two loss functions, occupancy loss and penetration loss. Both of our networks are trained using occupancy loss, which is an MSE loss computed using the ground truth occupancy supervision. Our context-aware occupancy refinement network is additionally trained using the penetration loss, which penalizes the refined two-hand occupancy values that are estimated to be occupied in both hands at the same query position. The lambda is a hyperparameter to control the weight between the two loss terms. Now we present our experimental results. We perform experiments in two main settings. In the first setting, we assume that the image and ground truth key point inputs are both available to test our model's representation power. In the second setting, we assume an image-based reconstruction scenario where only image inputs are available and the key points predicted from the input images are used. In both settings, we achieve the state-of-the-art results on Im2Hands 2.6M dataset compared to the existing single-hand reconstruction methods using implicit representation and two-hand reconstruction methods using mesh representation. We also qualitatively show that our method produces more visually appealing two-hand shapes. We also show our ablation study results with respect to each of the proposed modules in the image-based reconstruction setting. The initial occupancy estimation module alone produces two-hand shapes that do not look plausible due to the errors from the predicted two-hand key points. When the key point refinement module is added, it generates more plausible shapes. However, it still doesn't properly model hand-to-hand interactions such as finger contacts. Our full model, including the context-aware occupancy refinement module, reconstructs the most accurate shapes with higher hand-to-image and hand-to-hand coherence. For generalization test, we also show the reconstruction examples on RGB2Hands and Eagle-Hands datasets using our model trained on Im2Hands 2.6M dataset only. Our model is shown to be well generalized to the unseen datasets. For more details, please check our project website and code. Thank you for listening.